might I say. We're going to get started in continuing in the contaminants technical session. I'd like to introduce Evan Angus, who will be giving our next talk. So Evan, you can come on up whenever you're ready.
Yeah.
Yes, yeah.
Oh, it's still going.
Animations. Hold.
It shouldn't be moving. Pause it quick. Maybe it's the timing.
Like the animations are
Screwing everything up. I'll just, I can present off this, I guess, but like, I can present off like this guy. I don't know.
No, I don't think that'll work.
I don't know if it's the animations or what's going on.
Yeah.
There is animations, but there's not. Oh, okay. Oh, shoot, sorry.
That's okay.
I guess, yeah, that's what it is. Yeah, it's just.
Yeah, we just had, sorry folks.
I don't know if it's all of them. Maybe you kind of just check through just
Yeah.
to make sure. Thank you. Sorry for that.
Sorry, everyone. We just had a little bit of a technical issue with some animations. Just they'll roll ahead without Evan's go. So we're just going to fix that quick, and then Evan will get started. Thanks for your patience. That's good. That's fine. That's
advanced slide on most of it.
Okay, we're back in business.
Okay, perfect. Thank you so much. Hi, everyone. Sorry about the technical delay. Today I'll be talking about my work on factors influencing delivery of septic system wastewater effluent to tributaries. So starting off with a bit of background about septic system usage in Ontario. So approximately 14% of all Canadian households rely on septic system for the treatment of their household wastewater, with over 28,000 septic systems being used in the Lake Simcoe watershed and over 130,000 being used in the Ontario Lake Erie Basin. So we can see on the map, on the Lake Erie one, it really just looks like kind of one color, but those are all individual points which are represented as septic systems being used. So a bit of background of how septic systems treat our household wastewater. So residential wastewater is often has high concentrations of phosphorus, nitrogen, pathogens such as E. coli and emerging contaminants. When the septic or the household wastewater from the home enters the septic tank, primary settling of the solids occurs before the tile bed distributes the effluent evenly to the subsurface below, where further attenuation can take place. Once the septic effluent plume travels to the groundwater table, it mixes and then becomes groundwater. However, not all septic systems function properly, and we often see poorly functioning septic systems, such as a result of inadequate maintenance, poor siting, or increased hydraulic load by the household, causing ponding at the surface, leading to surface overland runoff of our raw untreated wastewater to nearby streams. Additionally, we may see septic system effluent being intercepted in the subsurface by subsurface drainage structures in our rural areas, such as agricultural tile drains, in which we intercept partially treated effluent and it's delivered as a rapid path or a somewhat rapid pathway to our streams, bypassing the correct treatment process as designed. Additionally, although illegal, some septic effluent may be intercepted by direct misconnection to nearby drains, bypassing either totally the treatment process or possibly just connecting the tile bed to a nearby stream, removing the attenuation processes that are happening in the subsurface. And although rare, we have seen some occurrence of this in the field, as shown with our picture of that drain. It looks pretty gross. That's what we think it is. However, these pathways are difficult to capture with traditional septic system inspections, which typically consist of tertiary walks over the tile bed, looking for wet spots or looking for breakout of effluent. So these interceptions by subsurface drains are often unable to be caught by preliminary inspections or re-inspection programs. So this leads me to the overall project objective, and we are aiming to develop the science and tools to estimate nutrient loads from septic systems to tributaries in the Lake Simcoe watershed specifically. And with this, we need an understanding of how much septic system effluent is reaching our streams and how this varies between different physical and socioeconomic characteristics across our watersheds. Again, my specific objective here today will be talking about my evaluation of the physical and socioeconomic factors and how these parameters can drive the amount of septic system wastewater reaching the streams. So our study approach, we have in total 53 sub-watersheds across the Ontario, Lake Erie, and Lake Simcoe Basin, as shown here. These represent sites of varying physical and socioeconomic conditions across our central and southwestern Ontario region. We then analyze these samples with various statistical methods. We then characterize each of our sub-watersheds with a variety of physical characteristics which are linked to septic system performance, such as poorly drained soils, percentage of septic systems on tile drainage lands, the area of the watershed, the drift thickness in our areas, setback distance. We also examined some socioeconomic characteristics we obtained from Statistics Canada, such as mean home age of occupied households and income statistics such as median household income after tax and percentage of homes on low income status. With our field data collection, we've conducted stream flow sampling and gauging from 2017 to end of 2023 across multiple seasons, with samples analyzed for nutrients, microbial tracers, and artificial sweeteners, with the focus of today's talk being on the HF183 DNA marker and the artificial sweetener acesulfame. So just looking at the two tracers I have to talk about today, the first being acesulfame. So the acesulfame is an artificial sweetener widely used in domestic household products such as diet sodas, toothpaste, and medicines. Is regarded as generally a highly conservative tracer in environmental settings, specifically through groundwater pathways. And with our acesulfame, we can see this tracer if the effluent is reaching the stream through all pathways, being groundwater or those failure pathways I previously had mentioned. In contrast, the HF183 marker is associated with the human gut microbiome and is unable to travel through groundwater pathways. So we're really able to look at more of the rapid failure pathways of septic systems where the effluent's not traveling through that groundwater pathway. Additionally, the HF183 DNA marker has a relatively short half-life in surface water bodies with less than 8 days in these surface waters, indicating that when we detect this tracer, we are seeing a recent emission of septic system effluent. And again, so with the HF183 marker, we are able to see when we're having these rapid misconnections or partial interceptions through drainage structures or overland transport as well. Just taking a look at the acesulfame distribution concentration across our 53 sub-watersheds, we can see that's highly variable, with some sites having quite low concentrations across all of our sampling points, and others with quite high, up into the 1,000 nanogram per liter range. Looking at now the HF183, HF183, we were unable to detect at all of our watersheds, but able to detect at all of our watersheds, and it was not always detected when our concentrations of acesulfame were high, so possibly indicating a different failure pathway. Additionally, on the plot, we can see the dotted black line indicates the human risk threshold value of 525 DNA copies per 100 mils, and this is from Bohem et al. And this was a study that looked to quantify or perform a microbial risk assessment of sewage contaminated waters. Using our artificial sweetener concentration measured in the stream, we're able to calculate the percent septic system effluent reaching the stream using the measured sweetener stream load and dividing that by the maximum possible sweetener stream load, which takes into account all the septic systems upstream and their theoretical maximum contribution. As we can see across the 53 sub-watersheds, concentrations or the median percent septic effluent varies widely across our study areas, with some sites ranging up into the 50% septic system effluent reaching the stream, and others below 10% often. We're able to use, due to our repeated sampling and due to our repeated sampling in the same sub-watersheds, we're able to use mixed effects modeling or statistical methods to try to associate these watershed characteristics with our repeated sampling design. First, we wanted to ask the question, what controls temporal variability? So we looked at two temporal controls between our sampling points. So this being the flow at which the flow at which our sample was taken, and also the season. And we see that under higher flow conditions, we are seeing more percent septic system effluent reaching the stream, possibly due to reconnection of disconnected stream branches, causing a flushing of the upstream branches, or also a possible flush over land of artificial sweetener concentrations or through the groundwater as well. Additionally, this correlates or corresponds to the seasonality we see as well, with the spring having the highest of our seasons of percent septic effluent reaching the stream. This is likely due to our high flow events are also primarily in spring. Then we wanted to check and look at which of our subwatershed characteristics are important. The first one I wanted to present is the construction date of occupied homes. So as we can see that as the occupied homes, as we get into an area where the occupied homes become newer, we're seeing less septic system effluent. So we're seeing older areas contribute more septic system effluent to the stream. This is possibly due to older homes having older septic system infrastructure and possibly exhibiting failure systems and needing to be replaced. Or we also may have longer septic system plumes from houses that have been constructed since the 1960s and have always had a septic system with a plume extending long towards the stream. The next parameter, which we found in our modeling, was the topographic slope. So looking at where the septic systems are placed and what is the slope at where they're placed. And we see a positive relationship with this parameter and our percent septic system effluent reaching the stream. And this may be due to groundwater transport of our effluent being faster in areas where we have septic systems placed on high slope. Next, we we saw that the percentage of households requiring major repairs exhibited a positive relationship on the septic system effluent reaching the stream, with the interpretation of this being that homes which are in need of major repairs, such as redoing a roof, are much less likely to prioritize maintenance of their septic system in those situations. So allocation of costs in those households may be towards more immediate or perceived immediate risk. The next parameter which we have in our model is percentage of septic systems on built-up lands. And we see this as a negative relationship. So as we get into more urbanized areas, we're seeing less septic system effluent reaching the streams in those areas, possibly due to urbanized areas having a more enforcement of their septic system management and maintenance practices compared to rural areas. And lastly, we saw the septic systems which are placed on areas of tile drainage. And again, this kind of relates back to my conceptual model, where in areas where we have septic systems placed on tile drains, we're more likely to have, or we could possibly exhibit, interception of the effluent, delivering it rapidly to the stream. Next, we wanted to ask if these parameters were significant for the HF183 marker. So we grouped our sub-watersheds in which, based on 3 categories: high, low, and very low or unlikely. With high being, with a watershed being categorized as high if we have had at least one sample exceed that risk threshold, as mentioned earlier. And with this, we can use histograms to qualitatively observe some preliminary trends. So the first 2 I want to just show here are the topographic wetness index and the construction date of occupied homes. So we can typically see that in areas where we have higher topographic wetness index, or areas where, or in watersheds where the septic systems are placed on higher topographic wetness index, we're seeing more of our high and low detection sites there, where we're getting detections of that DNA marker, possibly indicating that in areas of higher topographic wetness index, we're getting that flooding of the drain field and overland transport of the septic system effluent. Similar with the construction date of occupied homes, in areas of older occupied homes, we're seeing more septic system effluent, or more of that HF183 high detection in those watersheds, possibly indicating that in these areas, septic systems have exceeded their lifespan and are in need of replacement. Last histogram I'd like to show is the setback distance nearest the stream. The setback distance is commonly used to identify septic systems for reinspection programs. And here we see that primarily most of our sites within 300 meters of streams show the majority of our high and low detections of our HF183 detection markers. So really where we have septic systems placed close to the stream, we have that risk of microbial contamination with the HF183 and that rapid input of septic system effluent. So in terms of next steps, I'm working on completing a formal statistical analysis with the HF183 data to confirm the associated factors and to compare these factors with the factors that come out with the acesulfame-derived percent septic effluent models, to see which factors are important for the more chronic or through all pathways acesulfame and how that differs from the less conservative rapid failure pathway HF183 marker. Additionally, we are going to apply the statistical results to a regional scale geospatial tool to estimate septic system inputs and their associated phosphorus loads to Lake Simcoe and Lake Erie tributaries, which will be actually our next talk. So just like to thank everyone that's helped me throughout my 2 years. And yeah, I guess we'll move on to